Hello, my friends. So good job today. This was I love doing this as a way to sort of introduce you to some of the challenges in these kind of problems. There are a bunch of them. This symmetrical projectile scenario is one where we have an object, like we said, that starts at a certain height, is launched at a certain speed that we can call v initial at a certain angle that we call theta. Now, I wish you didn't have, I think you have all the vectors already drawn on here. I wish you didn't, but what are you going to do? Some things that we want to show, right? Off the bat, I might have to change this already. Yeah, I'm going to say that we want to make sure this is vi. Well, this vector that we just drawn in, hopefully you can recognize, is viy. Right? Sometimes we draw it over here, but for now I'm putting it back there on the left. Same vector, right? As long as it's that long and points in that direction. Same vector. All right? We also have, what went on here? Oh, I know what went on. Do I know what went on? No, I don't. Okay, well, the order of the animation. Isn't this a great video? Sorry. Yeah, some things to notice, okay? One big one. All right, if we look at all these components, and I don't know why this component isn't here, there should be a component that we call Vx. That the one thing we know about any projectile, whether it's horizontally launched or symmetrical or no matter what, but x components of velocities are always constant. All right, that's one thing. I mean, I can imagine asking you to draw these vectors on a quiz or test, all right? And the fact that we're drawing them all the exact same length is really important. It shows that the speed in the horizontal direction stays the same all the time, all right? Now, what's next? Yeah, the y components. Well, what do we know about y component stuff? Here's a real important word. This is a symmetrical projectile. So for a minute, if we forget about the vertical stuff, remember, it's really just like one of these that goes straight up and comes straight back down, but happens to be moving sideways the whole time. All right? So what I say is that the y components of velocity show the phenomenon that we refer to as symmetry of motion. And that means that if we know this VIY over here, a lot of you will remember that we have this VFY that's equal, what we call equal and opposite to VIY. Same exact size, just points in the opposite direction. Big deal there. All right? Now we know that this this vertical speed will get a little smaller as this object goes upward, right? And then anytime we look, again, straight across from that and use the symmetry thing, there's the same exact size vector just on the way down in the opposite direction. All right, and the other ones follow that same pattern. Big deal at the top, just like for something that goes straight up and comes straight back down, Vy is 0. Now, typically we have a VIY or VFY. I didn't put one there because we could call the top whatever we want. Sometimes we'll call it our initial place. Sometimes we'll call it our final place. But what I'm saying there is at the top, vertical velocity for one instant is 0. All right? Now, we're not saying that the object stops, right? Because it still does have this constant horizontal velocity. At the top, its direction or its motion is entirely horizontal for one instant. Okay? And yeah, if we want to look at the actual velocity or the actual speed, it's just like we did on the horizontally launched projectile. We look for the resultant of these vectors. All right, so I'll say it's the resultant of x and y components of velocity. All right? Notice at the top, there is no y component. So the whole velocity is just Vx. What do you think? It's okay? Okay. think fair enough to move on. Now, this launch angle and range thing, again, I think I, in the notes, gave you the components on here, which I sure wish I didn't. What are you going to do? So, launch angle versus range. Now, range, what we mean by range is objects shot like this, follows a path like that. We call this the range. Another way to say dx. All right, well, the question is, why won't an object... Now, something to notice here is the size of this vector and the size of this vector, same exact size. All we're changing is the launch angle. All right, so that's why it says launch angle versus range. We're not altering initial velocity. We're just altering the direction of it. Okay? So, why won't these travel far? Well, the only way to find dx is to do that. Right? It's the only equation we have in the horizontal direction. If we look at the components of that velocity in each direction, right? Here's vx, here's viy, because this is a vector that we'll call vi, initial velocity. Right? What's wrong with this one? I mean, why won't this thing travel far? It sure does have a big horizontal velocity, which is a key to having a big horizontal displacement. However, there's something here. Why is that small? Well, it's small because of this. Remember the other day we said time in the air, or just yesterday, depends on y stuff? It depends on, well, in this case, initial vertical speed. And since this thing isn't shot upward very fast, it has a small hang time, right? So I'll say that this one up here has, example 1 has, we'll say this has a fast Vx, but a small time in the air. All right, you can go as fast as you want horizontally, but if you're not in the air very long, you can't end up going very far horizontally. Now, this is worth pointing out too. The one on the top here, it might do something like this, boom, and it hits and then bounces and bounces and bounces. We don't talk about any of that stuff. It's only a projectile until, just, from the instant that it leaves the launcher until the instant just before it hits the ground. So forget about what it does after that. Okay? So with small time in the air, right, this part's small, therefore dx is small. Well, what about this one down here? How come this won't spend very long in the air? Or sorry, how come this one won't go very far? Well, it won't go very, very far again because if we say dx is vx times t, this one has large time in the air, but a very small vx, right? There's its vx. And no matter how long you spend in the air, if vx is really small, really short, really small, your horizontal displacement, dx, is going to be small. Okay? But this one, it will go nice and far because here are our components of velocity. Now notice, the horizontal component of velocity here, vx, is not as big as this one, right? And viy here, which links to our time in the air, is not as big as this one, but the mix of them is nice, right? So it has a, I'll say, pretty big viy, so therefore pretty big time in the air, and it has a pretty big Vx. So when you mix those things together, and both Vx and t are quote-unquote pretty big, we can get a big dx. Make sense? So there's some magic angle that if we set our launcher at that angle, it's going to fire our projectile the longest. You guess what that angle is. Report back to me tomorrow. Okay? All right. Now, Three things we'll ever have to solve for in a problem like this, in a symmetrical projectile problem. Can you think of any? What could I ask you? Well, I already did ask you, really. I asked you in the activity we did today. The one thing I could ask you to find is max height, which I call dy max, and that's this. dy max, right? Y vertical. We'll get to the next column in a minute. Other thing we could ask you to find, well, we could ask you to find this, which we call range. Range. Really, variable dx. And the third thing, you can't really label on here, but the third thing I can ask you to find we'll call hang time. Or T in the air, or T total or something like that. Okay? Now, when I say depends on, I mean X stuff or Y stuff. Well, max height. Max height depends completely on Y stuff. How high something goes has nothing to do whatsoever on how fast it goes horizontally. All right, depends only on Y stuff. All right, like, I mean, it depends on VIY. It depends on, well, A. It depends on, well, big deal for this, right? If we look at maximum height, you know what we're given? If we want to know max height, right, this location right here, what I would typically say is that VFY is 0. Right? If we can find what VIY is, and we know that AY is G, and we know that VFY is 0, then you can find dy max with one equation. We'll show you that in a slide coming up. I'm going to skip down to the bottom here. But if we do hang time, well, that's another one. Time in the air, we've said that a couple times now, depends only on Y stuff. All right? Again, like VIY, VFY, A, stuff like that. Okay? Again, nothing to do with horizontal stuff at all here. Now, dx, right? I get it. You see that and you say, oh, well, dx must depend on x stuff, right? Well, it certainly does. But remember, the only equation we have here is dx is vx times t. And t, right, depends on y stuff. So this is the hard one. And y stuff. Range problems for you guys will always first be a time in the air problem, and then you'll bring that time up here to find range. Okay? All right, let's go through one of each of these problems. And I give you an initial velocity here. I give you a launch angle. Let's find time in the air. Okay? Now, every problem that we do with these, every problem that we do, I'm going to have one of those. A vertical side and a horizontal side. And the first thing I'm always going to do is I'm going to find Vx and I'm going to find VIY. Right? Hopefully we remember that if we draw this triangle, here's Vx, here's VIY. We got to be able to do this, right? Vx is Vi cosine theta. VIY is Vi sine theta. Hugely important. And most of you, like I said, on the quiz, seem to do very well with that. That's great. Okay, so if we do Vx is, I wish the numbers weren't so big, 23 meters, 0.5 meters per second times the cosine of 37.5 degrees. We get that is, let's see, oh, of course you all have your calculators out and are calculating away. Wonderful. Right, I agree, 18.6 meters per second, right? You can even throw that in there if you'd like. VIY, VI sine theta, or 23.5 meters per second times the sine of 37.5 degrees. VIY 14.3 meters per second upward. Okay, now any and every single projectile problem that you do, we will always put over here that A is G, downward. Now there's one trick, and there's a couple ways to do this. There's really like 3 ways to do this, but the way that I usually do it is I go, oh yeah, this is symmetrical. That means for us, I'll do this. Symmetrical means that VFY is equal and opposite to VIY. Boom, boom, boom. Right, so that means that VFY, we've already found it, is 14.3 meters per second downward. I hear you. Can I just use the top and find the time to there and say VFY is 0 and then multiply my whole? Yes, you can do that. This is one of the ways to do this one. Okay? If I want to find T now, I can. I have enough information. I can use this stuff, put it in one equation, and say that VFY is VIY plus GT. Or VFY minus VIY equals GT, so we get this. Okay? Now I'm going to say here, sure, let's call positive stuff upward. All right, so VFY, that means VFY is going to be negative, and G is going to be negative, and VIY will be positive. So this goes negative 14.3 for VFY minus 14.3 for VIY divided by negative 9.81 for G. And that's something like 2.7 seconds. You all calculated, of course. Something like that. Okay, what do you think? I tell you what, the biggest deal is, notice, this is not just, you're really never going to put one of these right into an equation. You're only ever going to use this stuff to first find the components, and then the components go into equations, right? Because notice, this is, let's see, VFY downward, VIY upward, G downward. Okay, we can mix ups and downs in one equation, but you can never mix like a VI this way and a VF this way and a G this way in one equation. Couldn't do that. Of course not. Okay, so there's a typical hang time problem. Yeah, sure. Next, a typical vertical dy max problem, max height problem. Well, just like we did before, x, y. We already found, let's see, Vx, I don't remember, VIY 14.3 meters per second upward. All right, just going from before, right? Can I assume that we know how to still do that? VIY is VI sine theta. Now, big deal here. What's the one thing we know? We know for sure at the maximum height, we can say that VFY is 0. Ding, 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 ding. Okay, big deal, big deal. We've been doing that already, right? Ones that we shoot straight up in the air and come straight back down, we'd say, oh yeah, velocity at the top is 0. Same thing here, just the vertical part is 0. All right, for every single projectile, this is true. I already made it negative. I'm keeping my convention where positive stuff is upward, and therefore downward stuff is negative. And we actually have enough already to find dy. We can find the equation. Ready? Go. Find it. Find it. Find it. Get your reference table out. Press pause. Don't come back until you find your reference table. Good, very good. Now you've played again. So we can say that VFY squared is VIY squared plus 2G dy. VFY is 0, that whole thing goes away. Negative VIY squared over 2G is dy. Now, we've got to make sure we know it's that. It's not negative VIY squared, it's negative VIY squared. There's a difference. Because this does come out negative in the top, and we have a negative in the bottom. Our dy comes out positive, that's what we want. So we get negative 14.3 meters per second squared. No, just meters per second. Come on. Squared divided by, don't forget that too, negative 9.81 meters per second squared. You might want to make sure you put parentheses around the whole bottom. Calculate. 14.3 squared. I'm going to say that's about 206. Let's see, 14.3 squared. 204 and a half, not bad. Divided by 2 times 9.81 equals 10.42. Call it 10.4 meters. Okay? That one's kind of the easiest one, I think. Well, you're going to say the next one's easy. We want to find dx. Yep. Vx. Ooh, I don't remember. 14? 18.6. When Vx we found before 18.6 meters per second. Make sure you know how and why we did that. Range, dx. Only one equation we can ever use to find dx. Only one equation with any x stuff in it, and it's that. So that means we have to find time in the air. Well, we already found time in the air. All right? So we found time in the air using this stuff. I think we got 2.7 seconds or so. Well, remember, time is the one thing we can use on either side. So we bring time over here. Well, then we just plug it in here. dx, 18.6 meters per second, times 2.7 seconds. Calculate. Ready to go? Yes, yes, yes. Continue pressing the buttons. Equals 50-ish meters. Boom. Yeah, this one looks super easy, right? Well, it is, as long as you've gone through the trouble of finding t. Finding t, probably the hardest one. Probably. All right? So those are it. Those are the three problems. Those are the three kinds of problems with symmetrical projectiles. All right? All we really have are those three variables. How far, how high, how long to spend in the air. So we're equipped now to do some harder problems, that sort of mix up a few of these ideas. But the fundamentals are the horizontally launched ones and the symmetrical ones. All right, so in class tomorrow, this is your homework. Just take these notes. In class tomorrow, I'm going to give you a sheet of problems with symmetrical projectile stuff. You will tackle them with ease. and yeah, then we'll be ready to test pretty soon on projectile motion stuff. Okay? Okay. See you.